Welcome back, everybody. Today we're going to look at a new topic called the dot product. All right. In prior lessons, we looked at a few operations that you can use with vectors, things like adding two vectors, subtracting two vectors, multiplying times a scalar. Adding, subtracting, multiplication, you probably have a decent background in. All of these answers resulted in a vector. All right. Now we're going to study a new operation. This operation you probably don't have a lot of experience with. If you don't have a lot of experience with vectors, it's called the dot product. So if I have, let's say I have vector u, which equals, let's say element 1 is u1, u2, and then I have vector v, which is v1, v2. If I do u dot v, that's going to result in you take the first elements, multiply them, so u1, v1, and I'm going to add that to multiplying the second elements together, u2, v2. And when I add those together, I get a single number. I'm going to call that L, let's say. And that is going to be your scalar answer. If your vector is in 3 space, for example, if we have, right, our 3-dimensional vector, so I have u3, and then not u3, but v3. We just extend our dot product to say u3, v3, and then it equals L. Either way, if you're just doing the dot product, it's going to result in a scalar answer. So let's go right into an example. So I have example 1. Let's say I have vector u equals 2i plus j minus 2k. And vector v equals I minus 3j plus 2k. Should be little hats on these if you're writing your vectors in linear combinations. All right, so now let's say I just want to do u dot v. First thing I know is that my answer is going to be a scalar answer. All right, so I take my first elements, that is 2 times 1. Then I'm going to add that to 1 times negative 3. Then I'm going to add that to negative 2 times 2. And so that 2 times 1 is 2, minus 3, minus 4. And that's going to equal negative 5. So that is the result of my dot product. All right. Now, we don't always have to just do a dot product of u and v. We can do, for example, u dot u if we wanted to. And so I can take my first element of u times my first element of u plus my first element in this, right, second element, times my second element, and then add that to negative 2 times negative 2. So that is 4 plus 1 plus 4, and it equals 9. So there is another example. So let's say I want to do something with multiple operations. So I have u dot v, and then I'm going to multiply that times vector v. All right, so the first thing I know from the above answer is that u dot v is negative 5. I don't necessarily need to redo my math. I'm fairly confident that I'm doing okay. Then I'm going to multiply that times vector v, so that's I minus 3j plus 2k. And what we see is that this, because we're doing multiplication here, not dot product, our answer is going to be a vector. So negative 5i, then plus 15j minus 10k. All right, so now that we've got a little bit of experience in how to do the dot product, we're going to talk a little bit about how the dot product gives you some information about your vectors. All right, and the first thing that we need to know is that if the dot product of your two vectors, I'm going to call them u and v, u dot v, if it equals 0, then vectors are orthogonal. All right, orthogonal is kind of another word for perpendicular. It means that when these two vectors come together, they will indeed create a 90-degree angle. So let's see. So the way to determine the angle that your vectors make is, here is the formula. So I have cosine of theta equals u dot v over the magnitude of u. I'll make a better u out of that, times the magnitude of v. Now, magnitude was something we did in a prior video. If you need to review magnitude, that's fine. Just go back to the old video and you can review that concept. But what you notice here is that if my numerator equals 0, my denominator equals a number, I'm going to wind up with cosine of theta equals 0. And where does my cosine of, so where does my cosine equal 0? It equals it at pi over 2 equals our theta. All right, so you don't have to go through necessarily all these steps, just knowing that if that dot product equals 0, you have orthogonal vectors. All right, so if you're in a Calc 3 or math analysis class that uses calculators, you might use this formula a little bit more. If you're in one that doesn't use them as much, might be a little bit less. All right, so let's do a couple of quick examples. These are ones where you wouldn't need a calculator necessarily. So let's say for u equals 3, negative 1, 2, and I'll use the next line because I'm probably going to run out of space. 1 comma negative 1 comma 2, or excuse me, negative 2. We'll find the angle between each pair of vectors. Actually, you know what? I'm going to put one more vector in there just to make sure that we have all our information. And vector w equals, actually, we'll call this vector, this is vector w. And we'll call this vector v is negative 4, 0, 2. All right. Find the angle between each pair of vectors. All right. So let's say A is the two vectors are U and W. And part B is going to be and we'll just do part A for now. All right, so for U and W, basically I need to do cosine of theta equals U dot W over the magnitude of U, the magnitude of W, which is fine. So why don't we do it at this point? At this point, why don't we pause the video, take quick practice doing the dot product of U and W, and we'll see, we'll give you the answer on the back end. All right. So if you did the dot product of U and W, right, I get 3 plus 1 minus 4 gives me 0. And then the magnitudes, I got square root of 14, square root of 6. All right, well, at this point, no, 14 times 6 is 84, but 0 over any number is still going to equal 0. So if I know that the cosine of my angle equals 0, then I know from my unit circle that my angle equals pi over 2. All right, so now I'm going to add another vector into this. I'm going to add in vector z. All right, so I'm going to say that vector z equals 2, 0, negative 1. And I'm just going to put on the screen again vector v because, right, vector v equals negative 4, comma 0, comma 2. All right. And what I'm going to be looking for is the angle between v and vector z. All right, so let's remember our formula. It is the cosine of theta equals v dot z over the magnitude of v and the magnitude of z. So let's do the dot product. Let's also do the magnitudes. Pause the video for a minute. I will give you the answer on the back end. All right, so hopefully you did your dot product okay. Hopefully you got just a little bit more practice doing your magnitudes. For my dot product, I have negative 8 plus 0 minus 2 gives me negative 10. That should be your dot product, and my magnitudes were square root of 20, square root of 5. If you're having trouble doing any of these operations, I definitely suggest you go back and practice. Things like dot product and magnitude are going to reoccur throughout your course. So if I work on this a little bit and simplify, I get just negative 10 over the square root of 100, right? And the square root of 100 is 10. So I get cosine of theta equals negative 1. And I know that if the cosine of theta equals negative 1, then theta equals pi. All right, so there are two particular examples where you would not need a calculator, because for the most part, for these two exercises, your theta lands on your unit circle. If your theta did not land on your unit circle, you would definitely need a calculator to finish this problem off. Because of this formula, there is an alternate way to do a dot product. Not something that I would recommend, because you can do u dot v equals the magnitude of u, magnitude of v, times the cosine of theta. This is acceptable. I said not necessarily a recommended formula in a Calc 3 class. All right. So the next thing I want to do is vector projections and component projections. All right. And I always had a hard time explaining this to students. And I saw another teacher explain it in this way, and I thought it was really great. All right. So let's say you're walking your dog. All right. And you're starting at point P. Right. And you walk your dog along vector W. Now, your dog may have a mind of its own if he's anything like my dog. And he's on a leash, so he can only go so far, but he kind of strays from your vector and walks vector V. Right? There's only so far he can go, but he's walking, you're stretching out your arm. So what we can say is that vector V, that the dog is walking, is a projection of vector W. Because basically you're walking vector W, you're not deviating from that walk, and he is projecting a new vector. So you would say, excuse me, the way you would write that mathematically would be not GJ of V onto W. All right, the component of V onto W is the magnitude. So is the magnitude or scalar projection. All right, so let's try one or two examples, and then we'll call it quits. All right, so let's find the projection of U onto V if U equals 3i minus 5j plus 2k, and I'll write V on the next line. It's okay. V equals 7i plus j minus 2k. All right, so the projection of U onto V is going to equal U dot V over the magnitude of V squared times vector V. And your answer is indeed going to be a vector. All right, so why don't we pause the video at this point. Let's do U dot V and the magnitude of V squared, and we'll talk about the answers on the back end. Okay, hope you took some time to do U dot V. For U dot V, I got 12. For the magnitude of V squared, I got 54, which basically is I was doing the magnitude, but not taking the square root. And now I want to multiply that times vector V, which is 7i plus j minus 2k. Now 12 over 54 can be simplified, right? Because 3 goes into both of them. So I have 4. 3 goes into 54. So that's 2. Right? And then so 3 goes into 54. Excuse me, not 2, but 1, and then, so, excuse me. So 3 goes 1, so that's 2, It's 2, 18 plus j minus 2k. And you can basically just distribute at this point. So why don't you take a minute, distribute, and we'll see what we get. All right, before you distributed, I hope that you took that down to 2/9. 2/9 times, all right, and then 7i plus j minus 2k. If you didn't, that's fine. You would just have a little bit more simplifying right at the end, but your final vector at this point would be 14 over 9i plus 2/9 j, and again, the hat should be there, minus 4/9 k. And there is your vector. All right, so last example. Let's find the component projection. All right, so find component projection. And I've seen some books call this scalar projection because you're going to get a scalar answer of, and I'm going to change up the letters, B onto A. All right, so if B equals 1, 1, 2, and A equals negative 2, 3, 1. All right. So sometimes when you use the same letters all the time, people start to rely on it. So I'm changing up the letters. So if I do the component of B onto A, I'm going to do A dot B over the magnitude of A. And you can see that the formulas are similar, but again, if your dot product is going to give you a scalar and your magnitude is going to give you a scalar, you're definitely going to get a scalar here. All right, so why don't you guys take a minute, pause the video, do your dot product, do your magnitude, and we'll talk about the answer on the back end. All right, hope you took the time to do the dot product. I got negative 2 times 1 plus 3 times 1 plus 1 times 2 all over, and in my magnitude I got square root of 14, so that winds up being 3 over the square root of 14. All right. So there's a little bit of a start in how to do the dot product. I would definitely recommend more practice, but hopefully this will give you a few skills that you can work with. Thank you very much for listening, and I'll see you all next time. Have a good one.